Hello and welcome in the video. In this video, I will be telling about a project that we have, me with my group have developed for the AI-driven classification of skin lesion. So before starting of the technical part, I'm just giving some brief description. So like the skin lesion is kind of any abnormality that can form on the skin. This can be in two types. One is cancerous and one is non-cancerous. So there is clear like the cancerous category, melanoma, BCC, and ACC, and there's a non-cancerous category. So what happens like in the global perspective, this might be the risky position. This holds the nearly 1.79% disease that contributes the skin disease. So like also the category like melanoma can be deadly, it's life threatening. There is a statistics given like how many people died in the particular year. So like it's very important to be able to classify the skin cancer or the skin disease, and AI is here to help. So we have developed a project or a model that can classify the skin lesion based on a data set. So there's the starting. Let's go into the detail. So here's the detail of every skin lesion categories, like the description, how it appears and how it gets treated. So let's go to our project. So here's the first one. Okay, for the sake of the project, probably I will not be running all the code cells because it will take a huge time if I just run all the code cells. I will be running only those that are necessary. So the first thing is that we will show some sample photos. We have already told about those skin lesions. So we will be telling here now about the some photos from each categories. We have 8 categories. So this is the code to load the sample images. So what the library we are taking OS library to get the path of the folders of a PC, and we will using PLT matplotlib to plot the data and plot the image, and we will use also peel from image. So this is the base directory is the directory where the my data is saved. So this is the folder. If I just show it as the folder all the images, and if I just go into one of it, like this is the various types of images of this category AK. Okay, so there are eight of those. Okay, so let's back to the code. So we have selected this base directory and we have given the category. So these are the 8 different categories. So from here this code is trying to this code is first create a subplot of 4 by 4, so it will take 16 images, and this is the like title and the subplot, the adjustment for the space, and by this code it will generate the image, and it will take first two like until 2, so 0 and 1 index, so first 2 images of all the categories, and it will plot it. So let's run it. I'm running it. Let's see how it shows. The code is running. It will take a bit while as it is the first time running of this project environment. So now we can see that the code is running. It's showing the time here for how long it's being run. So after running for 33 seconds, we have got this image. So this is the output. So it's showing two initial image of each category. These two images are from AK, these two are from BCC. So these are the things. Okay, let's go for the next one. Now we will be started working on the real project. So we will load the necessary libraries here. So that the libraries that we are using here are categorized those as general categories, like OS for like operating system handling, like the image path and the folder path. So warning is handling the warning, NumPy, Panda, Seaborn and Matplotlib for the visualization, and we are taking test and split level encoder from sklearn and matrix to track over the progress, and from the keras we are importing image processing thing. The to categorical, it will convert to one hot encoding, and image to array is it will convert an image to the array. And for the model building, we imported the sequential so that we can create dense network, and we have imported this convolutional 2D max pooling to develop the convolution network, and we are using L2 regularization, and we are also using reduce on plateau and early stopping so that it can adjust the learning rate and it can stop early if it stops learning. Okay, so and also we have data imbalance. We have to balance the data. That's why we are importing this library, and this is a style. Okay, so let's load this so that we can run. So you can see after running for 2 minutes and around 20 seconds, the libraries, all the libraries has been loaded. Now let's go to the next one. Here we will define the dataset path. So I'm just giving actually the dataset path so that it can read the data. So if I just run it, it will be running so easily. So it's showing like it has 10 files, the 10 files like the 8 categories and 2 CSV files, and it has 25,331 individual files inside of it. So it's total images. So now if I just go for the count of images, so let's have a look how many images we have in those 8 folders. We have this code here, and I have already run it. We will run it again. So like this like code is taking the path of those base categories and these individual categories from here. Okay, here we have given individual categories and base directories. So what it is doing is joining those two and making a like full path, and from the full path is counting. Okay, and it's taking every photos like which ends with jpg and .png is showing those. So from here it's showing by this by this plt.bar is showing this bar chart, and here's the bar chart. Now we get the count of all the categories. We have 8 categories, 3 4 5 6 7 8, and we can see we have highest number of images from NV category. We have melanoma categories 4500 something. We have lowest images for DF and VSC and SCC. Those are the categories. Okay, so let's move forward. Now as we have very less images compared to other categories, we will try to generate some images, realistic images of those categories to make this data set as a balanced. So what we can do, we can use this generative adversarial network. This is an image generation model that can be used to generate realistic image. How it works? It works from those two principles. Like it will be trained on the real data set, and the two thing will work. So I'm showing it here. So this is the usual declaration or the like what we can do. We want to do these 3 categories to like generate realistic image from those 3 categories. So we are dividing, and also we are giving like in which resolution we want to generate image. So we are like declaring here 28, so it will be generate 28 by 28 images. So loaded dataset shape. Okay, so it has already read by this code. It has read from those 3 categories from this folder path that there are already 1120 images, and images are there. Okay, and it has already converted to 28 by 28 pixel. So now this is the code for building the generator. What it will do, it will generate some random image, and it will take this 100 as dimensional input. So like the noise it is, and from that it will try to generate an image, and those images will be converted through the layers for the keras layer, and on each layer it will go with patch normalization and leaky relu for optimized generation of the training. And here it's reshaping. After each layer it will reshape, like from this 7 to 7 it will stride 2 by 2, so it will be 14 by 14. Then from here it will be 2 by 2 again, so it will be 28 by 28 images. Okay, 28 by 28 output is showing, and the output it will be 10H activation. So this is the basic structure of generator. So let's go for the discriminator. So what the thing, it will generate random image, and this discriminator will learn from the actual image, from those 1120 images, and try to compare those images generated by this generator whether it is real or not. Okay, so that's the thing that the discriminator will do, and it takes the same output as the input as the output of this generator, so that it can compare, and then it like generates, flattens those to the sigmoid with the sigmoid output. Okay, so here the developing the GAN model is the generator and discriminator compiling, and here we are training. By this code we are training this generator so that it can learn actually from the image first. So after we run it for the 1000 epoch, here we have mentioned is 1000 epoch, and we have given 100 dimension to reduce the to develop the random image, and after this 1,000 epoch, now we will generate some image. So we have given here to generate 15 images in total. So now you can see these are the images that is generated by the GAN network. So if we just look closely, we can see like in this photo, in this age, there is some shape like distant or not closely large, like on a far distance. It might be look like an skin, but overall it doesn't look like an skin image or skin cancer image. So probably this GAN network cannot learn it well. Probably it needs to be run for more epoch, or probably the image that we have are not enough to learn this pattern to generate image. So the thing that we thought, it will not be a good idea to use GAN for our work, so we will not use it. So we have written here, after even like running it for 1,000 times, it cannot produce realistic image, so we will not use it. We will work with our existing image that we do have. So now this is the code for block the image from the data set. So this is a custom function. It will take an image and it will reduce the image, or it will resize the image to 28 by 28, and it will then convert it to numpy array, image to array. Okay, so an image will be converted to an array by this function. So here is the function to load all the images one by one. So what it takes, we are using here threadful executor and tqdm. Threadful executor is kind of like it can take multiple images together, and by the tqdm we can track the progress here. Okay, so we will run it, then we will see. And this is the categories of the class folder that it will be using. Okay, so here it will take a bit time because it's loading all the images of 12,000 like from each category. So what we will do, as this NV category contains 12,000 images around, but our melanoma category, there is a serious category, have 4,500. So we will make it a bit justified. We will load maximum 5,000 images from each class, so that not more images are getting load from this class NV category, unless it will like be more imbalanced. So okay, so this is the same code just to load 5,000 images from each category. And okay, let's run it first. So it's working. Okay, I'm getting an error. What's the error? Load and resize image is not defined. Okay, so we have to run this custom function, because inside of it is processing each image by this function. Okay, so I have run it, then I am running it. Okay, now we are seeing it's loading those images, and after loading those images, it will convert everything to the numpy array. Okay, NP array. So it's combining. Actually, it's loading, converting it numpy array by this function, the defined function we showed earlier. So it's loading all the images now here. So let it be loaded. Now we can see it's like concurrently loading, because on those large bar we are seeing some small shape bar coming forward. So it's loading all those images. When everything is loaded, then it converts to the large black like a stride. So it will take a while to load all the images for us to work. Okay, in 54 like in near about 1 minute, we have loaded one category. Okay, so probably have very less images here, so it's loading very quickly for the third one also. Okay, we'll wait a while for all the images to get loaded here. Okay, in NV category now it's not loading all the images, it's loading up to 5,000 images that we declared here. After running the code for 3 minutes and 45 seconds, we can see that all the images of our like folders has been loaded and converted into the numpy array. Now what we will do, okay, we will check our images are now converted in the numpy array. We have x all and y all. Okay, in the x all we have all images. in array format, and in y all we have all the labels. So labels like for the NV, those categories, those labels. Okay, so we will check a random image from those like arrays, so that we to check whether it has been loaded properly or not. So if I just run it, we can see like it has been loaded a random index with the label to see. Okay, so we can see an image. This is an image. Okay, so our images are loaded into the numpy array successfully. So now it's a label encoder. So what it will do, we have data imbalance. Is it from somewhere we have a large amount of data, the images, so somewhere we don't have, so we will use this smartin from imblearn.combine. We will use smartin. So what it will do, it will take the numpy array and it will flatten those in the 1D vector, one dimensional vector. Then it will apply this smartin. So it will generate some synthetic, it is called synthetic minority oversampling technique. It will try to generate synthetic image, a synthetic sample from the existing sample, and then with ENN, editorial nearest neighbor, so it will also reduce or delete those are not that much relevant. So after running this, we have got this is the class distribution now. Okay, so we see it's kind of balanced, not fully. 4998, 4992, 4962, 4901, so 2941. So it's kind of like balanced. It's not fully imbalanced like previous. So right now what we have got kind of imbalanced data set for us. So this is the here we also use label encoder. Label encoder is means we have this category A, K, B, C, C. So for the machine to understand, we have to convert it to 0, 1. So by this it converted this, and we are checking here like which label has converted to which index. You can see here. Now it's time to do the test and split. Our data is now in this format: x reshaped. This is the thing: x resampled and y resampled. This is the final thing. We have x resampled and y resampled. So now we will split those from x resampled and y resampled. We will do the 10 trace split. So we have splitting those, and as our sum of our class has less samples, you see 2941, 2421. So that it splits the category in equal part, like where it is less it will also take this less but proportional amount to the test and train. So we are stratifying this by y sampled. Okay, and we have taken a random access so that it can generate the same result all the time. So after splitting those, we get our sample has been split in this way. So now we have x train, x test, y train, and y test. Now we will go to generate a CNN network. So for the CNN network, we have to convert this 1D array to a 2D size, because it process the images. Image has to be 2D, and in our case it has to be 28 by 28 pixel. So by this code we are reshaping the images from array to 2D, and now this is our CNN model. Let's look on this. We have convolutional network. We have three convolutional network: one, two, three layers. From the first layer, we have all the layers, our like filter size is 3 by 3. So it strides, it goes from one side, one corner to the other corner and to the end of the image to capture all the details or the features from the image. And on the first images, on the first layer, it will use 32 filters. In the second it will use 64, and third it will use 128 to capture more details. And everywhere it is using ReLU activation, and we are using L2 regularization to prevent overfitting. And for the first input shape, it will be 28 by 28, and all the after all the shapes, all the layers, we are using max pooling, so it only pulls the maximum features, and batch normalization to streamline or to make the process faster and generalized so that it doesn't overfit. So after three layers, what we are doing, we are flattening the layers so that it can be fed to a dense network or artificial neural network. So this is our CNN convolutional neural networks, the layers, and these are our artificial neural network there. So after flattening, we are dropping out some like 50% of the neurons so that it like to prevent overfitting further, and then we are taking 25 256 neurons and converted to 128 neurons, converted to 64 neurons, and finally as we have 8 class, so it is output layer is 8 class with softmax activation. Okay, before that we used railway activation. This is the standard thing. Now this is the CNN model. So what we will do, this is the summary of our CNN model. So with this we will use adaptive, like Adam optimizer is good for the adjusting the learning rate, and as we have multiple categories, so you are using categorical cross entropy and you are using accuracy matrix. So now we are also using reduce on plateau here. What it will do, it will adjust the learning rate whenever it will see that the validation loss is not improving for the three layers, three like run, then it will adjust or it will reduce the learning rate. And for the early stopping is whenever this validation lot will stop improving for the five layers or five steps, it will stop running the model because there will be no scope of learning anymore. So now we are running it for the 100 epoch. So after running it 100 epoch, this is the outcome we have got. Now it's showing from the accuracy, training accuracy it got 99%, so it's like learns use kind of like overfitting thing, it learns everything. And in case of validation, it has got a pretty much good score, 96.96. So in this category, like in this split, it can work very well. So okay, now we will save the model here. So this is the Keras model saving way. We have saved the model. Now what we will do, we will plot the performance by this code block. We are plotting the performance, and we see that for the training and validation loss, we are kind of get in this 20 epoch or kind of 40 epoch, we have reached in the ultimate position. It improves further by a small amount, and we run it for 100 epoch, and still it's learning, but it's very like negligible here. You see, there's not that much improvement. But in case of validation accuracy and training accuracy, we got the best result at our 95 epoch. Okay, here we have got the best result, unless after that is getting dropped. Okay, so now we will plot our accuracy. So from the test and y test, we are plotting, and we see that our model has got 96.96% accuracy. So pretty good here. So now by this code block, we are plotting the confusion matrix. So we can see in all of the cases our model is performing very good, like somewhere it's achieving the perfect score. But we have also one concern. In case of melanoma, it's only achieved 80%. It's not that much like promising or good here. So in case of confusion matrix, we can see like most of the cases they have classified everything properly. But in this melanoma case, some is true level. Some melanoma are being detected by something else as BKL. This might be a problem in some BCC. Some of them are like classifying as SCC. Okay, and also the precision recall problem, we have something like it's not actually melanoma, but it's predicting as melanoma. It's actually BKL, but it's predicting as melanoma. So, but apart from those, it's pretty much good. Okay, so we have got 96, like 97% accuracy from our this CNN network, custom developed CNN like layer. So we will try other model here. So we have tried here VGG16. So VGG16 is kind of a pre-trained model. It's already trained based on a large data set, image data set. So we just utilize that pre-training category, pre-training for our model. So this is the code block to train to use the VGG16 for our model. We are utilizing this base layer, and we are freezing the convolution layer. So the VGG16's models convolution layer work for us. Then we are building our model on top of it. We are compiling the model and we are running it. So we are running it for 20 times. So we see that after 20 epochs, we see that like after that we haven't got that much good accuracy, 66%. So probably VGG 16 might not be perfect for our case because we have a very specialized thing, skin cancer or skin lesion images. So we are considering not to use VGG 16 here. So we have like now we have saved our model. We have saved our model already previously. Now we will use it. So by this thing we are loading our saved model as a like object of loaded model. Okay, so this is the definition, the function by which we will convert any image that we will get. What it is doing, it will predict image, it will take that label encoder that you used earlier model, it will take a name of the model and image path, then it will load and resize. We have function previously, it will load and resize the image, and then it will take the dimension and it will feed forward this to the model. Okay, so this is the thing, model.predict by the image it will predict. So now we are predicting some images here. So we have taken an AK image and we can see it's been predicted properly with 100% confidence. So probably we have got very good accuracy on AK, that's why it's like so much confident. This is another image of DF, dermatophobia. It is also predicting properly, we got it. And this is another image of melanoma. We loaded and we are predicting. So it's predicting properly, but its confidence is low. So we saw that the melanoma category have only 80% F1 score. So it's true, it can happen. We have taken another image of NV. Okay, but in this case of image, we see that it's not predicting properly. It's predicting as melanoma, the NV image, and with high confidence. So this is the problem of the model. It cannot learn fully, like with 100% confidence. So we are taking another image of BCC and we are seeing that it's predicting properly. So that's it. So this is our custom developed CNN model to classify the skin lesion image. We have utilized this 2019 ISIC, International Image Skin dataset to for classifying this, and we can see like our custom developed model performs like really good compared to other model, and this can be used in the actual classification. Probably some more training, some more images, and some balances of the undersample category, gathering more images needs to be done to make it a perfectly tuned model. So that's it from us for now. Thank you so much.